This is an introduction of gamma ray bursts, putting it all together. Gamma ray bursts, also known as GRBs, are one of astronomy's current hot topics. The evolution in understanding these enigmatic events has proceeded every has proceeded very rapidly from the early discoveries during the Cold War to the current hypernova models and stellar remnant merging models of today. This project will go through the early stages of discovery, including highlighting the space missions responsible or detecting these events. Also covered will be some hand-picked GRB events to compare them with the current models. In the beginning, gamma rays themselves are not a mystery. In 1952, gamma rays emanating from astronomical phenomena were thought to emanate from interactions between cosmic rays and interstellar hydrogen Prensos. Prensos 2005. Gamma ray emissions were even detected from the Crab Nebula in 1961 by the United States satellite OSO-3. However, these were relatively lower energy in the range of 100 to 300 keV. Another U.S. satellite, the OSO-7, detected gamma rays from a solar flare in 1972. It wasn't until 1973 that gamma ray astronomy became a serious topic. During this time, the Cold War between the United States and Soviet Union was in full swing, and to determine if the Soviets were compliant with the Nuclear Test Ban Treaty, the VELA series spacecraft was launched to detect higher energy gamma rays, higher than those detected coming from the Sun or the Crab Nebula. While no atmospheric gamma rays were detected, gamma ray bursts lasting an average of 10 ms to 10s were detected in random directions on the sky rather than from the Earth, with no detections occurring in the same place twice. Early 2005. In order to solve this mystery, the COSB satellite was sent in 1975 to study these high energy sources of gamma radiation in detail. The above image from the ESA website demonstrates the existence of bright gamma ray sources sources within our galaxy. It was determined at this time between 1975 and 1982 when the COSB mission was active that the gamma ray sources were restricted to our own galaxy. The model of gamma ray bursts so far, because these gamma ray emissions were detected, the source of these emissions must be pretty strong, between 10 to the 38th power to 10 to the 42nd power, ERGS, ERGs. There was no known phenomenon to conform to these energy to this energy requirement except for neutron stars. While neutron stars themselves do not emit this much energy, their magnetic fields could provide the catalyst required to accelerate electrons fast enough and hot enough to account for this energy. Additionally, material accreted onto the neutron star, like a comet, asteroid, or some other piece of debris, could be heated to the point that such energy could be generated. This model seems to have been confirmed by the U.S. satellite HEAO-3 when when spectroscopy of a gamma ray pulsar was shown to contain a high energy spectral line of aluminum. Print source 2005. The aluminum spectral line from supernova was thought to be from supernova. A supernova within our galaxy seems to fit with the apparent brightness detected, since at least a 3 solar mass star is required to provide the nucleosynthesis to create aluminum. Charles N. Sword, 1995. The stellar remnant for such a star is a neutron star. A new development. In 1991, the Compton Gamma Ray Observatory was sent to explore a wide range of high energy astrophysics from 30 keV to 30 GeV. While this observatory carried 4 experiments, the most remarkable was the burst and transient source experiment, or BASTE. 2704 BATSE, gamma ray bursts. What was discovered was that GRBs were not limited to our galaxy. Instead, a homogeneous distribution of GRBs existed in every region of sky. The image above shows 2,704 GRBs detected by the BASTE experiment. Basically, what this means is that the majority of detections by BASTE were outside the plane of our galaxy. It was only the resolution of these new instruments that allow rapid follow-up of GRB events to determine their location. Another remarkable observatory launched, launch, launched in the year 1994, the, the B POSAX satellite managed to capture the transient events of GRBs, sometimes within hours of detection, while the actual GRB event was not captured. The residual high X-ray afterglow was detected. This image is one such afterglow in the X-ray wave band. This afterglow can last up to a few weeks, early 2005, while BPO Sachs was able to actually pinpoint the GRB source. It was not able to catch a GRB in the act. The previous model of GRBs being the result of neutron stars and their magnetic fields may no longer be available. GRBs are bright, and if they occur well outside our galaxy, they must fit a new energy requirement, the magic number 10 to the 52 power to the 50 seconds power, 50 seconds power, ARGs or greater. There are no there are not many sources capable of producing this much energy, and this new requirement has placed the GRB as the brightest, most violent object in the universe. In most cases, a GRB will be brighter than the combined light output of its host galaxy. Friedman and Kaufman 2005. The 10 images below models what a GRB might look like and how long they last. The graph next to each of the images shows the average photon counts including the galaxy image, which is in the center of the image. The GRB occurs near the top. Notice the counts of the frame of frame 6 as well as the overall duration. This burst lasted only about a second. The relative short-lived event like this makes them very hard to directly detect them as they burst. Our only hope is to piece together a series of satellites to form a network to detect GRBs and to quickly slow slew a telescope to the source with the hopes of looking for either the residual X-ray emission or find an optical counterpart. The network that exists now is called the Third Interplanetary Network. It is the goal of this network to detect a GRB event within 10 seconds or less. Thank you, and I'll see you on the next one.